got a break. It seems that everyone is already here. So let me speak a little bit about the histograms and a little pet project of mine that is called physt. I'm glad that I was invited to Lithuania, to Vilnius. It's my first time here, and till now I've really appreciated everything that happened here. So, who am I? Who am I? I'm Jan Pipek. I come from Prague, and for a long time I was a physicist, but about 2 years ago I switched. I don't know whether that was a fortunate step or not. I switched to data science, and now I'm working in Showmax, which is a company that provides video streaming in all Africa. You can find me on GitHub or Twitter, or best way how to find me is to come in person to Prague, where we have PyData meetups. I'm one of the organizers. So let us speak about histograms. So probably all of you know what histogram is, but just to be on the same page, I have some like quiz. So do you think this is a histogram? No, it's not, because it's a visual representation of some relationship between two variables. Typically, if you have a bar plot of a histogram, it's just one variable. What about this thing? Is this a histogram? Almost, but from the probably statistical point of view, the histogram should show distribution of some continuous variable, while this is a categorical variable sorted in somewhat random order. The order is not really random because it's in alphabetic, but still, there is no real meaning to the alphabet. And what about this? It's almost a histogram, but as you see, it's not the nice bars, not these nice rectangles. It's actually a kernel density estimate, which is very nice and very smooth, but it's not histogram. So what about this? Yeah, finally this is a histogram, and this is the thing I will speak about in my talk. Why histograms? Histograms are very nice because when you receive a bunch of data and you want to see very quickly what is the attributes of the data, you just create a histogram and you just know what roughly the distribution of this variable is, and it's really painless. The good point, which differs histograms from, for example, the kernel density estimates, is that they are precise and that they are compact. Once you have the bins really defined, then the number that is inside the certain bin is really the exact number of occurrences that you had. And it's compact. If you want to somehow to export your histograms or save them, then really the only numbers that you're saving are the bin counts and the edges. While, for example, the kernel density estimate just needs all the points beyond it. And again, I'm getting back to step one. Now you're not in the role of someone who is exploring. Now you're in the role of someone who is presenting your data. And the good point is that almost everyone understands visually what a histogram is, and you can show it even to people that are not statisticians or physicists or scientists. But what is the situation with histogram in Python? So if I come to some problem that involves computation in Python, I typically start with the numpy library. Probably everyone does. Is there someone who does not use numpy here? Okay, not a single hand, so you are ashamed, probably, to admit it publicly. So if I have numpy, there is a nice function that is called histogram, and I just call it, and let's see what happens if I put the data, which was some kind of distribution of weights of people of a certain country called fake land. So I receive a tuple of two things. The first thing is a numpy array that contains the bin contents, like the frequencies of the occurrences that were found in each bin. And the second thing is an array of edges, like the left and right edges of the bins. That is nice, but it's probably difficult to work with when you, for example, want to keep this relation between the two arrays and, I don't know, you want to modify them. Then, if I want to plot histograms, again, like the most popular graphical library for visualization in Python is probably matplotlib. So I use matplotlib that also has a nice function that is called hist that can produce a plot like this. It's either immediately shown to the screen or written to some file or shown in your IPython notebook depending on how you use it. And this function also returns something. It duplicates the thing that numpy does. So again, the contents and the edges, and also a list of some graphical objects that, if I know correctly, are the rectangles that you typically see in the graph. So again, it's a tuple of 3 arrays, but I think that histograms deserve a bit more. I think that they should receive some proper object-oriented treatment. I think that, do you remember what were the edges, what were the values of the edges between the bins? It was something like 173.665 and such. So probably I want the computer to provide me with nice bins if I ask him politely. I think that it should be able to modify histograms, so add new values or anyway, just for them just to be dynamic. And I think there should be more like plotting options for them. So that's how I started physt. This is a project that I started when I still was a physicist, and unfortunately I had a lot of time, or fortunately, and so in my like job time I was writing this library. But since then, luckily, still I still have time, and the project is not dead yet. Probably now I should just mention that I want to enhance matplotlib and I want to enhance numpy. I'm working on them, based on them, and yeah, I really like them. And I was also partially motivated and inspired by a computing framework from high energy physics that is called Root. There are some concepts about object-oriented histograms there, which I basically take from them. Just another disclaimer, there is a lot of nice histogramming libraries written in Python that you can find on the internet, or you can find them linked from the project page, which, speaking of which, you can find physt on GitHub, or using this QR code, or you can install it just using pip. Unfortunately not Conda, because I'm not friendly with the setup for how it is done, so maybe later. I don't have time for that. So I will now speak briefly about the four things that I was missing with histograms, and just describe how physt deals with them. So first of all, the object representation of the histograms. I try to mimic numpy a bit in the way that if I call some function, I receive something, and I put the same arguments as I would put in the numpy histogram function. I receive an object that contains answer that numpy would do. So in this, if you want to make a one-dimensional histogram, I have a function that is called h1. If I call it, now again on the same data that I used previously with numpy, I receive an object that is of type histogram 1D. It's like you see the representation, it shows how many bins there are, what is the total number that is inside, and any information about the type that is used for storing the values. Now, it's a class, so it probably has some attributes, it has some methods. So basically from, if you want to get back to what numpy answers, you can access the property frequencies that returns exactly what numpy did. I have an attribute that is called bins that returns something different. In principle, physt supports also bins that are not consecutive. It's probably not, the use case for this is not very broad, I think, but still it supports. So when you get bins from a histogram here, you receive both the left edges and right edges if you want to get something similar to numpy, then you call numpy bins or just edges. Because it's an object, you can store more information inside than just some bunch of numbers. You can also store some metadata that is then useful when you want to plot the histogram, for example. So in here I store the name, I store a title, and I store the axis names, which these are three probably similar things. But then if you plot this histogram, you see that the axis name is used for the axis down in the axes. The title is used at the top of your plot, and if you have, for example, multiple things displayed, then the name is used in the legend. Of course, histogramming is not just for one dimension, and it's not for the one dimension also in numpy, so you can have more dimensions. So let's say that to the height numbers I also add some more variables. I add weights that are a bit correlated, and let's say intelligence, which hopefully is not correlated with height, although I would be lucky if there is some positive correlation. And then you can create histograms with multiple dimensions. So for example, the two-dimensional histogram is created when calling the method h2. Here you see that's another object that is of different class, but it behaves similarly to the histogram 1D. Typically, if you want to visualize 2D histogram, you visualize it using a heat map, which you show here, and you will see also some more examples later. You can create a 3D histogram, which A3. Here I want to show also another thing, that if you, for example, have a pandas data frame and you have properly named columns, and then you create a histogram out of it, the column names are automatically used for your axes. So then if you plot different projections of that, the axes are automatically used. Again, it's and now the 3D class is not called histogram 3D. It's a generic histogram ND class that allows you more dimensions. And 3D visualization is quite complicated unless you create some transparent voxels or use some sliders in your interactive way. It's probably difficult to visualize this, so it's not supported in physt anyway. So if you have really many dimensions, you can have as many as you want. The method is called h, and there is just one warning, because I'm not using sparse arrays, so you can imagine that if you multiply the numbers of bins in each of your directions, then the amount of memory grows exponentially with your dimensions. If you want, I've also added an experimental feature that's called a collection that keeps multiple histograms together with the same bins. So then you can, for example, put them together, or I don't know, just manipulate with them at the same time. But it's experimental. If it's an object, so you can do more things with them. There is JSON serialization of the histograms. If you write your histogram and you have a physt that is not more than about 1 year old, then you can read the file and like receive the object as it was defined. And so if you have like gigabytes of data and you produce histograms from them, and they are only a couple of kilobytes or megabytes, then it's also maybe a good way how to send them further. Now, if histograms are, of course, not just like objects from the, let's say, Pythonic point of view. They also are some kind of mathematical objects, and they can be treated that way. So you can, for example, you would be interested in adding two histograms together. Of course, you can do it if you have arrays in numpy, but in here you can just call histogram 1 plus histogram 2, and you receive a combination of them. So if you add people from fake land and true land, you have, let's say, distribution of heights in in some other country. That's the union of them. What do you think? Has multiplication of histograms have any meaning? Probably. I'm not clear what that would mean. So if you try to do that, you will receive an error that it probably doesn't make sense. Of course, you can hack it. You can take the arrays out of the histogram and multiply them if you're really confident that you are doing the right thing. So the operators that are supported is additions. Of course, you must have similar bins. It doesn't make sense to add histograms with different binnings. So in such case, of course, you also receive an error. Subtraction is supported with some warning because like negative frequencies is also somehow hard to interpret. And the multiplication and division is possible by scalar. If you have a multidimensional histograms, you can project them into lower dimensions. So starting with our 3D histogram that contains two variables, you can project them into two. So now you have a 2D histogram that you can plot finally. You can also project into, for example, one dimension. Another thing that is quite similar to projection, but it's not. It's actually slicing the histograms and taking pieces out of them. You can index the histograms almost like NumPy. Also, I think some kind of masked arrays is also supported, but now there are some issues with that. So I would just stick to numbers and slices. So if I just take a second slice in the first dimension of the 3D histogram, I again receive a 2D histogram that I can plot. Now you see that it's a bit different than the projection. I can like now I have two numbers in the index, so I'm just receiving one-dimensional histogram like this, and I can also like do some funny slicing, and this, as you may imagine, then I have slices in all three dimensions, so I'm getting back again a 3D histogram. Now this is like three numbers, so it means that I'm getting to a scalar. And the scalar is not just the number, it's also like the edges of the bins. I've found that a bit more practical than receiving just one number. And okay, so now the second topic was that I didn't much like the randomly looking numbers that were presented for me as the bin edges. So first of all, let's start with just really automatic way, which the NumPy does, and I just do h1 without any further arguments, and that's what I receive. It's like the numbers of these numbers. But you see that I was not accessing the attribute bins, but binning attribute that leads to the internal implementation. All like bins along all of the axes are represented as binning objects. There are different binning objects. Some of them are like really copying what NumPy does. Some of them are not described like this in this static way, but are more dynamic, and so on. So in this case, just again the random numbers. But if I know, for example, that I want bins that are 2.5 centimeters wide. I call h1 with two extra arguments. One of them is like a string fixed width. That's, let's say, a type of the binning, and the other argument in this case means like what is the width of the bin. So when I call it, I receive another object that now is like prescribing like the way how the bins are computed, not just the bins themselves. And if I look at, and you probably see it from the picture that the bins are aligned with the numbers like 160 and 180 or 200. There is a bit even more, let's say, automatic and probably pleasing way. I don't know what width of the bin I want, but I know that I want roughly 15 bins, let's say. That's for some reason. I selected this number, and I let the computer decide what the width will be. I call this algorithm, let's say, human, which is like it's human targeted, and it will automatically find for me that like the ideal bin width that produces this amount of bins roughly, it should be 5 centimeters wide, and there probably should be 19, which is like really close to my original 15. I can go even one step further and just call it human without any more arguments, and in such case it's like selects some automatic number that is ideal for the number of values that you have. There is some theory behind it that you can, for example, find in Wikipedia or numpy documentation that just specifies what is the best number. And if I do this, I get 10 bins, 10 centimeters each. That was like the normal numbers, but let's say that now I'm investigating the number of children each person in my country has. You see that this histogram is looking pretty weird, and that I have like strange gaps. And that's because I have 10 histograms for like 7 different values, which is probably not so fortunate. And for this particular case of low integers, I have a special, let's say, algorithm that is called integer that like takes the bins, centers them around the integers, and automatically sets the width to 1. So now, if you have this, it's fine. If you're having numbers like 7 million, then probably it's not the way to go, because you will have 7 million bins, and you don't want that. And another problem is that if I have a huge range, for example, I have data about the population of all countries in the world, 200 numbers, starting from a couple of hundreds and going to China's population of 1-point-something billion. And if I want to put them in one histogram, and again, not specifying any further arguments, I receive 10 bins, that one of these bins contains almost any country in the world. There is like six countries that are of medium size, then maybe 2 of a middle of even larger size, and then I have India and China in one bin. That is not fortunate again, so that's why I have an exponential binning algorithm that automatically finds the edges that are placed regularly in the logarithmic scale. So now this is getting better. Only the numbers are a bit weird again. If I want to have nice bin edges, up to now there is no human exponential. For that you need to really find your bin width. But again, physt helps in that you can specify the number of bins and the range, and then it's automatically calculated for you. And so in here, the numbers are reasonable. So that was about the bins. And the third main topic is the dynamic behavior of histograms. Histograms should not be read-only, because let's say that again I have this little country of fake land, and I have a nice distribution of heights of the people there, but then I move there, and what happens, I can either recalculate the histogram again from another array, but what I can do is just add one value to my histogram. So that's I'm using the left bit shift operator for that, or you can, if you're not happy with these strange signs, you can use a method called fill, and you will see that the total number of values in the histogram grew by 1. And if you remember precisely what were the contents of the bins, you see that one bin grew a bit. Okay, that's fine, but let's say that not me, I'm not tall enough, but 200 really tall basketball players move in, and I try to fill them in the histogram. That's easy. I don't use fill, but I use fill_n, and I update the histogram. But you see one problem. I would expect the total number of values to be 1,201, but the number is a bit less, and you probably spot the problem. My range is too narrow, and the histogram probably would make use of a bit of widening. This is possible if your binning is set to adaptive, which can be done either through the adaptive attribute of the histogram, or just when you call the h1 function, you can specify it as a keyword argument. Then, whenever you fill it again, and you go outside of your range, then the range is automatically like widened for you. You can even start with no bins at all and have just 0 values, and then like create the histogram on the way. Yeah, and that's another way how to do that, is that if you have two adaptive histograms that have different ranges, but the ranges are comparable and the bins can be matched against each other, you can add them, and then also the range is shifted. If you're not satisfied, it's just one funny like functionality. If you think that you have too many bins, you can like merge them together, so that's then you can have less bins. Like for example, 1 bin. That's probably the happiest, because it's very precise and very meaningful. Seriously. So that brings me to the last topic, that is just visual, and there is not so serious. I tried to include some easy plotting in the physt, and I tried to make it a bit general enough to support different plotting libraries. Most of the functionality is developed for matplotlib, but there are some like attempts to bring something to Vega and Plotly and Volume for some special data. It would be really nice to support at least one of the interactive libraries, either Vega or Plotly properly, but I don't have enough power to do that. So I will show you just a couple of matplotlib visualizations. So the typical, if you want to plot something in physt, you can either call the plot method of a histogram, or you can use the plot as a proxy in a similar way how pandas does that. And then if you take this proxy, then you can call the different methods on that will call the proper visualization type. So if you want a bar plot, you just call the bar method. If you want a step plot, you call step. If you want a scatter, you call scatter, a line, and so on. What you can do is you can show the values. So now I'm getting a bar plot that is the default option, but I'm adding values. I change the color. I specify the line width. I can end the error lines. That adds, given some conditions, make sense in this like if the bin contents are really randomly and probably normally distributed. I'm not sure what is the exact condition, but if these are fulfilled and if it's a really random process of generating the variable, then these lines have some meaning. I can show some total statistics. That I can plot 2D histograms. Again, the default option is to have a heat map, which can have lines, don't have lines, show the values. You can change the color map that is used. You can hide the bins that don't contain anything. You can make the color map based on logarithmic scale, and that's it. As I mentioned, if you have more dimensions than 2, you're out of luck, but you can project or slice into 2D or 1D. Just so that this is not just really only theoretical, I just show you 3 simple examples how I really used physt. First, this is a this is a project that we did in one of the hackathons. We had like gigabytes of different temperature measurements at different times, different days of the year, in different places in one of the cities in Czech Republic called Brno. And what we were interested in is how the temperature develops during the day based on the months. So that was like, I think in the end we created 4D histograms that we were projecting and slicing, in which physt really helped. So you see that in January, typically the temperature in Brno is like 0 degrees plus or minus something, not depending on the hour basically. While in July, the situation is completely different and you have like a huge peak during afternoon hours. Another thing was, again, when I was a physicist, I was not procrastinating all the time. And I really produced some results with this. And that was, we had neutrons produced in a beamline, and we wanted to like somehow visualize how they occur on the surface of of this beamline. And this is where physt was helpful. And yeah. And the last thing I did for my friends, I collected all the finishing times of people that participated in Prague International Marathons and like created some distributions from them. And using physt, I was able like to visualize it properly, and I found some strange, interesting things. Like most people, a lot of people wanted to be just below 4 hours, and if you look at the finishing times, you just see this pattern that like you have a peak building up towards 4 hours, and then like in the next minute there is a very sudden drop. So that means that probably the people achieved their goals, or the ones that did not maybe died, or I don't know what. and that's basically all. And so I wanted to show you that histograms can be represented as objects, that they can have nice bin edges, that they can be dynamic, and that then they should be easy to plot. And this is the last thing I want to show you. Do you know what that is? Do you think it is valid Python syntax? Actually is, and it's some Unicode sign that shows this. But unfortunately, that's called bar chart, and a histogram does not yet have its unique Unicode symbol. I would be happy to have it. So thank you. Yeah. So any questions?